This will be the last presentation this year in the series on the Dirac equation. It's about an idea I got in the beginning of May, I think, of treating the gamma vector itself as a dynamical variable. We have the action, the geometric action. I'm told that this was discovered by Hilbert the day before their conference in 1912 on the geometric theory of gravitation, that naively differentiating this gave the Einstein tensor. And it still stands. Einstein used some time or some years trying to figure out what to do with the higher derivatives. That's solved now. I know for sure that one professor knows how to do it, and it's in some book, but I've never learned it. Well, then the matter action, we use the Lagrangian for the Dirac equation. About prerequisites, gamma is operating on psi, and gamma is a vector, so it differentiates in the direction of gamma. That's standard notation. Physicists usually write gamma I psi, but this is more succinct. This guy is the scalar product. I explained it at some length in the video on the legacy Dirac field, and in the next video I introduced the alternating scalar product. Using the scalar product alone, it gives an interesting theory that's just not the particles that we see in our universe, and introducing the alternating scalar product seems to produce the particles we know in this universe. So that's the one we'll work on. You see, gamma occurs in the action. So when we can treat the geometry as a dynamical variable, why not treat gamma as the original dynamical variable? That was my idea. I will report today what I found out, and it's quite unfinished, but promising. Of course, we have the connection here between the gamma vectors and the geometry. This is the metric tensor, or rather the tensor equivalent to the metric tensor, metrically equivalent to it as a vector times a vector. It is necessary that they are combined this way, and that's because of Dirac's discovery of the way he proved that the gamma vector is Lorentz invariant. Lorentz invariance, that is a feature of the tangent space at each point. And in that tangent space, we shall have generators for boosts and 3D rotations. Dirac made formulas for the generators based on the commutators, and to prove Lorentz invariance, the anti-commutators had to give matrices that are a constant times the unit matrix. And then it follows that gamma itself is Lorentz invariant. So that's a very nice result. And that means that this requirement is essential, that the anti-commutators of the components of gamma become matrices that are not only diagonal, but also have the same numbers at each place. Let's start taking the derivative with respect to gamma to see what will the law of motion become. Doing that is rather bored because there's no guarantee that the wave equation for gamma that we end up seeing will ensure that the components, the LT commutators of the components, actually become these diagonal matrices with the same entries. But now let's just try and let it flow freely. So the derivative of gamma bar with respect to gamma in the direction of delta. I'm sure you know how to find directional derivatives, and if you want to see more on directional derivatives with respect to fields, you may want to check my first video on deriving boundary conditions. There we do this in both simple and complex connections. Or rather, I do it, you can see it. You must differentiate the action with respect to gamma in direction of delta. And here delta is an object like gamma. It's a vector field of matrices. We use the chain rule. We take the action and differentiate it with respect to G bar, and then apply it on the direction G bar will move when we when we operate with delta in the direction of delta, differentiate in the direction of delta. We do the same with the matter term, and then we have to do it with this guy as well. Again, the chain rule. This result is already known, thank God. And then we just have to put this in, and the minus here comes out here. And then square root minus g, the volume element, just write dv. And this guy is easy, it's just replacing gamma with delta. And this doesn't really matter, because L matter tends to vanish. We have written here the directional derivative as a symmetric form of delta here as well. We need to write this as a symmetric form of delta as well. To do that, there wasn't room for dv here. To do that, we use the definition of the imaginary part minus the complex conjugate divided by 2 times the imaginary unit minus divided by I gives I, which we multiply into each term. And then we must change sign here because this must be conjugated. Now we can write up the derivative. So we just take out delta and delta. This is more difficult because here we have a matrix operating on this guy to give a vector, and then the scalar product on that. So I've suppressed the A as well here. That gives the sign of psi. If you don't know what I mean by this, then just forget it or check the video on the alternating scalar product. But it's not needed to understand the computations that I do in this presentation. I just wrote up this intuitively. and then it has to be like operated on by delta symmetrically. That's a little weird maybe, to clash two matrices into one number. On the other hand, writing this up, I thought that this was the usual psi dagger, making it to a row vector and then conjugating it. So I had pluses here. I had an odd feeling that this guy wasn't Lorentz invariant. And then I realized that the dagger symbol had not only to communicate with the matrix multiplication, it has to communicate with the scalar product as well. So it must be like this with the two minuses on third and fourth component. And knowing that, it's easy to prove that this is a Lorentz invariant guy. This is the wave equation that this vanish. There's no derivative of gamma visible, but of course the derivatives of gamma occur in the Ricci tensor and scalar tensor. Does this make any sense? As I mentioned, it's a very bold move to let gamma flow freely, but it has to be tried. And we try it by making a nice example, an easy example. The one I chose was a Robertson-Walker geometry with a Dirac field. We stipulate that gamma has this form, and then the spatial components, gamma x, gamma y, gamma z, they depend only on t. A surprise is that gamma fails to have vanishing divergence. Square root minus g is the determinant of the coefficient is minus c squared f to the sixth. This is the square root then. And then to compute the divergence, we multiply the temporal term with this, differentiates with respect to t, and then divide by it again. So it gives 3 f mark f squared divided by f to the third, 3 f mark divided by f, and 1 c and gamma naught. So that's the divergence. Next, one needs to derive the Dirac equation when gamma has non-vanishing divergence. We actually get a surprise term there. We need to verify that this is a solution. Differentiating this with respect to t and putting it gives, of course, mc squared psi. And this guy gives minus 3 halves, blah, blah, blah. And that will exactly cancel with this term, 3 halves. So, interesting, isn't it? And that, of course, gives a density that in an expanding universe will diminish. This is the example. Next, we need to find out what is the wave equation for the gammas. Actually, it fails. We need to find the Einstein tensor. I found it in this book, which I like very much. It's a mathematics book, but they explain the physics thoroughly not in great detail, but thoroughly. And I like that, they take it quite serious, that physics is difficult. I tried to find the formula in Miesner, Thorne and Wheeler, which I couldn't do in 5 minutes, so I gave up. But this is the tensor. I want the Einstein tensor to be dimensionless. And you can see here, this is velocity squared and velocity squared, so they cancel, and dx, x, y, z, that's the coordinates in the original R3 space, which is used to form the warp product here. So they're dimensionless. Then we operate with G on gamma. That's just inserting gamma. We know gamma naught, but the other coefficients are just gamma x, gamma y, gamma z. So this should have dimension per meter. This cancel, and gamma x, gamma y, gamma z has dimension per meter. And you can check that this works out as well. I have checked the dimensions of all the formulas, by the way, but I just wanted to give you a little push to do it yourselves, being very explicit about some of the dimensions of some of the symbols I use. We need to compute this expression. So we differentiate, first we take the differential of psi, only dt occurs, because it only depends upon time. And this guy, of course, gives minus I mc squared divided by h bar times I, there we are. But we must differentiate this as well, minus 3/2 f mark per f times psi, and then the I. In the symmetrized product, this will cancel, because we take the adjoint. So when we have a diagonal element, we need to conjugate it and add it, so they will cancel. Therefore we only get this term and one entry. And this one entry comes from this guy. Now we are ready to write the wave equation. These two terms must, or some constant which is negative, times this plus this must vanish, and then this must vanish by itself. And since these guys fail to vanish, this expression must vanish. And that's easy to solve. This is the solution. So we are in a Friedman space. And the temporal component becomes this. And that's where the contradiction is obvious. So the free-flowing gamma did not work. This may agree, then this won't, and this definitely won't. Maybe you will be able to find a way to make it work. Instead of doing that, I went in another direction. I said, let's put maximum constraint on the gamma. And what could I think of here? my idea was to use only the original gamma matrices and say that gamma must be a linear combination of these. So that's a maximal restriction, ensuring that the symmetric product will make sense. And I compute the symmetric product here. We take just one component and naught 1, and the symmetrized product, so it's plus 1 naught, and just use the definition. There we see we have f naught I, f naught j. So in this term we exchange I and j to obtain this. Then we have this anti-commutator of the Dirac equations. So when I and j are distinct, it vanishes, and when they're equal to naught, it becomes 1, and otherwise minus unity. We will have this to be equal to minus the metric tensor, so I define this to be minus the scalar product, where it's defined this way. And then I write it this way with these symbols, sign symbols here. This is just an idea. I don't say there's no claim that this is the right way to do it. Of course, when if the theory seems to work, or people will work more on it, then we should collect the coefficients here in a geometric object, and that's probably going to be the vector, the tangent space tensored with R4 with the product given on the other page. I felt that that would be too complicated with several scalar products being available, all in the same presentation, and some of them being new to you. So to make it a little more simple, we just treat these coefficient as independent fields, and they are real, and they are a function on the space-time, so it's a real field. Then I would like them to have the same dimension, physical dimension, say no dimension, and then since gamma must have dimension 1 divided by length, and they have no dimension, then the partials should have dimension 1 divided by length. So partial naught is 1 divided by c partial t, and these are dimensionless, so the x naught is f x, and the partials then 1 divided by f. That's the first remark. The next is that I've defined gamma with 16 coefficients, but the geometry has only 10, so there's room for some reduction here. One might impose a symmetry requirement on the coefficients. I have no opinion on this. And then an interesting thing, which surprised me quite a lot. I checked if it was so, just in case, because we can consider gamma to be the square root of minus the metric tensor. So what about the square root of the determinant of the minus the determinant of the metric tensor? It actually turns out to be the determinant of the coefficients of gamma. I find that interesting. I don't know if it's useful, because we still have a 1 divided by the determinant in the volume element, but Interesting, isn't it? We need to do everything again, differentiate the action with respect to the FIDAs. We write the metric tensor as a sum, and then differentiating with respect to FLM in the direction of delta. Now delta is just a real function. From here we get the term where I equals L and K equals M. Differentiating the other one just comes by a symmetrized tensor product. Then we are ready to differentiate the action with respect to di. This is the formula you already have seen. Now it's just differentiating with respect to these coefficients. And when we plug in this guy, you see we just plug in each component by itself. That's because we know that the Einstein tensor is symmetric. This is obvious. And here we do the same. The metric tensor is symmetric. In this formulation, this is our wave equation. This guy must vanish. We see that it's coupled equations. And of course the higher derivatives come in here. Back to our example. We take the one in the middle first. It only gives something when we differentiate with respect to time, and then only gamma naught gives anything, so that gives the Kronecker deltas here. I and j must be naught both to obtain something. L matter will vanish. We write up g again, now with these coordinates that have dimension 1. Have dimension length, so this is length squared. You may be more used to seeing the Einstein tensor of Robertson-Walker geometry like this, by the way. Then we plug this in, and since it's symmetric we can just use this and this guy. It's diagonal as well. It means that I and K must agree, so there's only we must the sum over k cancel, only I gives something, so that is it, but we need still to sum over the j's. When I vanishes, we'll get a term here, non-vanishing term here. So that gives an equation. When I is 1, 2, or 3, this is naught, and that means that this is naught for the spatial component, but we don't know whether it comes from the sum vanishing or the coefficient vanishing. So that's inconclusive. The temporal component, that's interesting. That turns out to be the Friedmann's equation. So we know that we are in this situation, and that means that this coefficient vanishes as well. The point is that we have absolutely no conditions on the spatial components or the spatial parts of the gamma. Any combination giving the right metric tensor will work according to this theory. However, If alpha we have already stipulated, so we need to check whether that's true, whether that's consistent, and inserting the known results here, we get an equation for c to the third. I haven't checked that this actually agrees with the Friedman model, but I'm quite sure it does. This is the last video that I make this summer, not only because this summer ends tomorrow, but because now at the start of the academic year, I will go back to studying number theory. I'm about to study chapter 2 in this book, and I do that by solving all the problems in back of each section of chapter 2. There are many problems and I learn a lot. I like that very much. Then next summer I'll work on the next part of my project with the Dirac equation. The first part was to treat it as a classical field. Like any field, the classical field should be consistent and work. It's impossible to imagine one having a quantum field that does not work as a classical field. The next part is trying to make many particle theory the same way that has been done for, say, the Schrödinger equation, so that a two-particle state is a tensor product of two one-particle states. In this case, an antisymmetric tensor product, of course. I shall investigate that next summer. Whether I shall have anything to report, that's unknown. So this is goodbye for now.